let's revise back of what we have done so far. Anyone can tell me quickly how many power devices that we have seen so far? What are the names? Just list it down if you still remember. Come on, give me one.
Thyristor.
Thyristor. What is the short form for thyristor?
SCR.
SCR. And the full name for SCR, anyone knows?
Silicon control rectifier.
Silicon control rectifier. Thank you. Any more?
MOSFET.
MOSFET.
BJT.
Did we mention BJT? I think briefly, yeah. Any more?
IGBT.
IGBT. Okay, who is the new version of IGBT?
GTO.
GTO. No more?
IGCT.
IGCT. Finished?
Diode.
Diode. Any more?
MOS control thyristor.
Okay, MOS control thyristor. So basically, we list out everything already here. Now, can you tell me out of this, which one that we should use for juice maker or mixer? Anyone still remember? Juice mixer? Juice maker or mixer? Nobody? With the diagram shown here. What is that? Thyristor. Almost there. Any more answers? Still remember this page? Let's have a look at number 4 here. Who's the person that we use here? Which one is the power device? Triac, the name. You use it in juice maker, blenders, vacuum cleaners, washing machine as well, yeah, in the picture just now. Okay. Triac. Please remember how to draw the symbol of triac as well, okay? For example, if I gave you the application just now, washing machine, which power device that should I take? Which thyristors? Then you say triac, and then draw me the symbol of triac with the complete label. So you should be able to come up with this diagram. Okay. All right. Number 2. Let's go back to the picture. Okay. Right. Electric car. EV. What kind of power transistors or power semiconductor device should I choose for EV cars?
GTO.
GTO EV car. Any more answers? Sorry?
MOSFET.
MOSFET. Any more? C. when I say EV cars, right, there's so many parts in EV cars. So which part of EV car that you are referring to? Are you talking about the motor drives? Are you talking about the interface? Are you talking about the auxiliary supply? There's so many things in EV cars, right? So I'm talking about the one that drives the motor, induction motor. Okay. So induction motor is considered medium power, right? Medium power. So which one should be the induction motor that you have seen, right? Induction motor is AC or DC? AC. So AC unit what? Because EV cars is supplied by battery. Battery is DC. So from DC, I need to change it to AC. I would need to use inverter or rectifier.
Inverter.
Inverter. So what is the component that we use in inverter? Oh, you see the application here? Motor control. Yeah. Who is that? IGBT. Okay. In inverter, the component that we use mostly is IGBT. Okay. And what about the EV cars? The panel, right? Panel interface, the screen, etc. These are considered as the auxiliary components, right? Low power application. Then MOSFET may come in, right? Because of low power application. IGBT is in the medium power and medium frequency. MOSFET belongs to high frequency and low power. And then if we're talking about traction, electric, this is not car, this is train. Traction. Okay, traction belongs to high power and quite low frequency. So they use what this range of GTO option. Okay, triac, we mentioned this one before, right? So please be familiar with this diagram and put it in any information that is not being shown here from the previous slide so that you can take it as a summary to revise back. Right, let's continue. This is also another example of a comparison table of these different power devices, IGBT, medium power, medium current, but the frequency is not shown here, right? Maybe you can add it in. The rest are shown to compare among the different devices. Okay, so today we're going to further discuss on the Chapter 1, Introduction on New Devices. So this is the new topic on the development in power semiconductor devices or power switches. What is the new material that used to form or to fabricate, to manufacture the power devices, or in short, the switch? This is known as the wide bandgap material. Wide bandgap materials here, we have two. Number one is silicon carbide. Number two is gallium nitride. Please remember this symbol, SI and capital C, GA and capital N. If you see SI, what is SI?
Silicon, Prof.
Silicon. And now silicon plus carbide become Si and capital C. Gallium nitride, also GaN. When they were discovered in the early 21st century as part of the semiconductor device, semiconductor material. When we say semiconductor, right, if you still remember in your power electronic devices, you learn about the gaps, bands, right? You have the conducting bands, you have the insulating band, and then you have the band gap, right? So the diagram, it looks like somehow this one. So you have first, second, this is the band gap. So this is the electron, the energy that you need to cross from the bottom is what? Insulating. And the top one is the conducting. Okay, so the atom that normally in the normal modes, they are all in the insulating, meaning what? Cannot conduct current. Then if you want to make these atoms become conductor, or you want to make the material become conductor, you need to supply energy to the atoms so that the atoms is able to jump to where? Jump across the band gap so that they can come to the conducting band, right? So this conducting band is depending on the material itself, whether it's a short band, just a small river. If you're a big gap, then it become a big river. Then you need more energy to jump across the big river. So these materials belongs to wide band gap. So this band gap is actually big. Okay, so silicon carbide and gallium nitride belongs to very large band gap materials. So what is the benefit of having large band gap or big wide band gap? Anyone? It's given in the slide. Okay, here, bigger band gap energy, larger breakdown field, higher saturation velocity. These are the features or the characteristics of these two friends, or we know it as a wide band gap materials, silicon carbide and gallium nitride. What are the characteristics again? They have high power efficiency. Efficiency is good. Meaning what? If efficiency is good, is what?
Power losses.
Power loss is minimal, very small. Okay, we want that. It can operate in high operation or temperature condition. You see that many of our electronic devices today, right, we put it under the sun. Under the sun means if it is tropical countries like Malaysia, in the afternoon, and then it goes throughout the day. Imagine that what is the temperature that the components inside the electrical device has to withstand, right? High temperature. So it works in high temperature, and it's able to be conducted in high switching frequency. What is the benefits of having higher switching frequency? You see that this diagram, right? They go on like this. The frequency has to go on. Why? They want to improve the capability of devices, that they should be able to work in high and higher frequency. Higher frequency means that in 1 second, they can operate many, many more cycles, right? Frequency is the number of cycles in 1 second. Okay, anyone knows what is the benefits of having high frequency? It can reduce, it can help to reduce the size of the material, as well as to reduce the power losses as well. Provided that the conducting loss is minimal. So these are the benefits of having wide band gap materials, right? Compared to the conventional silicon only. Okay, compared to silicon carbide and gallium nitride, their performance in terms of power efficiency, temperature operation, and switching frequency, they are much better. Okay, better. In how better is that? Let's have a look at the picture. You see, this picture is in the form of a frequency on the x-axis, and y-axis is the capacity in volt ampere, or the power. So you see that the conventional silicon limit is the gray color line here. See, it says that the limit of the silicon, and then silicon carbide and gallium nitride came in. So they expand the limit from, can you see the line? Let's see. This is the original limit of the conventional silicon. So this limit has been raised or improved further up. Cannot see the color. Going up means the frequency is going further up and the power is going further up. Okay, meaning that these materials can be used to manufacture switches for higher power application. Okay, for example, the wind turbine that we mentioned previously, because the development of wind turbine capacity is increasing from year to year. So if you come out in another 5 years, the wind turbine is very big and you don't have a proper switch to operate that wind turbine, so cannot die. So it will halt or it will stop the development of RE because your power electronic power switches cannot go further. So they came up with this invention to improve the power capability is important, as well as to be able to operate in the switching frequency of higher range. Okay, what else that is written here? Okay, that all the research. Okay, so if you look at this diagram, make it bigger. The power semiconductor devices family tree. What can we see here? The comparison of the conventional silicon, well known. We have diodes, transistors, thyristor, and all the families under it. Just now we mentioned about diode, MOSFET, IGBT, GTO, IGCT, MCT. Okay, so if you're using the the new version of a silicon, which is a silicon carbide, what is the short form for silicon carbide? S small I, capital C, and gallium nitride, Ga, N capital. I would expect in your test or final exam later, right? Maybe you will not see the full words of silicon carbide. You only see this one. So make sure you know what is this. Maybe Si is for silicon. GaN is gallium nitride. Okay, they have the same family tree as well. So they have diode, transistor, thyristors, diode, transistors. All the new families came in with the features of wide bandgap. What are the three things that we mentioned for this family? Wide bandgap power semiconductors or power switches. They are having, what is the characteristic? In terms of frequency, no. Let's start with the efficiency. Higher efficiency means lower losses, higher efficiency. And number two, they are able to operate in high temperature. And then they also can operate in high, what is the third one?
Frequency.
Switching frequency. All right, right. Three important features of the new family. We call it the wide bandgap family. Okay, now 1, 2, 3 of this. Okay, pictures that depicts, and I think this is a very interesting picture here down below on the right hand side. It summarizes the characteristics of silicon carbide, and gallium nitride in a spider diagram like that, pentagon. And you guys, right, the graduate attributes that you guys have, right? For example, I'm not sure how they measure, and then they plotted in this diagram as well. So a higher voltage operation, meaning that high power application. Who is able to work in a higher voltage operation? Let's see the blue line, and this is maroon line. Maroon line is able to work in higher. Blue also, compared to the orange line, silicon, the conventional, or the existing power semiconductor, the range is smaller compared to the new wide bandgap, right? Energy gap. And then what about the frequency? Higher switching frequency, yeah. The range of the blue lined silicon carbide and the maroon lined gallium nitride, better. And last one, you see that temperature. All right, temperature application, you see that only the silicon carbide is the winner. Okay, gallium nitride seems to be not that okay, not excelling that much compared to the conventional silicon. But then in terms of higher voltage and higher frequency, this one is good. And overall, the total winner goes to the silicon carbide because all these three, it's very good. But then if you compare in terms of this, it's a bit smaller, but still much better than the conventional silicon. Okay, overall, we can say that these two materials, silicon carbide and gallium nitride, has given much better improvement in terms of the three performance parameter, power application, power capacity, higher temperature application, and higher switching applications. Okay, example of silicon carbide MOSFET and silicon carbide Schottky diode. This is the real picture and the drawing and the symbol at the bottom there. Okay, that's all for the part 2. Yeah, we still have 2 more slides or PDF to go. So before we close this one, anything that you would like to highlight or discuss? Let's proceed to the new topic here. It's written here, gate or base drive circuits. The keyword is drive circuit. Gate or base, it depends on which semiconductors you're talking about. Base, normally you have, if it's a BJT, there's no gate, isn't it? There's a base. If it's IGBT, there's no base, right? There's a gate. IGBT. Okay, it depends on what types of semiconductor device that you're talking about. But what is drive circuit here? What is the function of drive circuit? It's not driving a car. It's driving the circuit. A question came in. What is driver circuit? Drive is the common term. Driver is the circuit that doing the work, right? It's not the one that driving the car. That one is driver for vehicle. This is the driver for a circuit. What is the driver of the circuit doing? Written here, circuits that are constructed to turn on and to turn off the power devices. It provides an interface between the control signal, which is the control signal, and the power circuit. And sometimes it's called the gate drivers. You see driver circuit, gate drivers, and then drive circuits. Basically, they are referring to the same material or device. Okay, it's the same person. No, it's the same circuit. Driver circuit, gate drivers, they are the same thing, right? What they do, they are supposed to help you to turn on and turn off the power device. If you still recall that the differences between ideal and practical. There you are. Ideal switch, do you need to have large power to turn it on? No. Maybe you only need the signal of 0 and 1. Or sometimes you only need 0, 5 volt. This is a signal. 0 means turn on. No, 0 means you turn it off, shut it down. 1 means you turn it on. For ideal case, maybe you have 5 volts just to turn on. Fine. But in practical, it depends on the different switches. IGBT, what do you need? Plus 15 volt, right, for the VGS. And MOSFET as well. You need 15 volts to turn it on. If I supply 5 volts, do you think that the IGBT will turn on? No, it will not, because it's not able to turn on the practical switch. Requirement is you must have 15 volt. So in general, the voltage driven by the practical switches requires substantial amount of current and voltage, and voltage to turn on and to turn off. Okay, that is the requirement. So how do I make sure that the IGBT can be turned on? I only have the signal. See, I only have the signal 0 to 1 or 0 to 5. So how can I change from the ideal signal here to turn on the practical switch? In between, I will need the help of driver circuit, DC. So this driver circuit is helping me to turn on the practical switch by receiving the signals. Let's have a look at this diagram. So the signals belongs to low power application. Okay, signals, or we call it control signal. It can be from 0 to 1, it can be 0 to 5, low power most of cases. So the control circuits do the control and give the signal. So the signal is here. If the signal is 0, so the control unit tells the drive circuit, okay, now you should turn off. How do I turn off this thing? Before we proceed, what symbol is this? Power switch. What is the name of this switch? Anyone here? Is it BJT? Diode? MOSFET? IGBT? What is the symbol? There's nobody here, so quiet.
IGBT.
What is that?
IGBT.
IGBT. Thank you. IGBT. What is the requirement for IGBT to turn on? Let's have a look. There you are, IGBT symbol. And the requirement says to turn on is, where is it? Is it written here? No. Okay. The requirement to turn on IGBT is 15 volts. I need to supply the GS 15 volts to turn on. Okay. To turn off easily, I supply 0 volt. 0 volt to turn off, to turn on 15 volts. If the signal that I control, right, and now I want you to turn off the IGBT, then I give 0. No problem, because 0 is supposed to turn off. Without the driver circuit also, I give 0, it will turn off because there's no voltage. But if I want to turn on, the switch, right? Make it on, close the switch. I give 5. The 5 volt is not able to turn on the VGS. Cannot. So the switch is still open. I cannot close the switch. I must have to step up the 5 volt into 15 volt. Who is doing the work from changing 5 volts to 15 volts so that this power switch IGBT can turn on the driver circuit? Okay, this driver circuit is converting 5 volt into 15 volts for me. Okay, this is your calculator. Depends on how you want to design the calculator. You want to control it complexly, simply. Okay, so they are all control operation here, giving you the signal. Then the driver circuit will do the job of amplification. It amplifies 5 volt into 15 volts. That's why the function of a driver circuit function is number 1, amplified, number 2, isolate. Only 2. Okay, you just need to remember 2. So what does it mean by amplification here? The function of the driver circuit or gate driver. It amplifies the control signal to a level that required to drive the power switch. In this case, the driver circuit is amplifying 5 volts to 15 volts so that the power switch can turn on. Okay, number 2, isolation. It provides electrical isolation between power switch and logic gate. You know, what is the common device that we use to do electrical isolation? Anyone? How do we isolate electrically? There's only one component. What is that?
Insulator.
No. Electrical isolation in is the what? What is this?
Transformer.
Transformer. The symbol is TX, not T-Rex, yeah? TX, transformer. Okay, this is the transformer. Using pulse transformer. This is pulse, right? You know, pulse is on, off, pulse. Okay, it's like your heartbeat also pulse. Okay, so this pulse transformer, what is the function of transformer? Isolation. And we also know that transformer is able to do what? Step up and step down of. What does it step down and step down? Up and down of what?
Voltage.
Voltage. Correct. Can I step up the power?
Cannot.
No. Please don't say the transformer is used to step up the power. Power cannot be step up or step down. You can only change what? The current or the voltage. The power is always remain, okay? Because why? We know that energy cannot be destroyed or created. That is the rules of the energy conservation, right? So power is related to energy. If you cannot destroy or create the energy, power remains the same. But power equals to I multiplied with V, right? So if you manipulate the voltage, the current will be changed accordingly to ensure that the power is always the same, provided there's no losses. If there's a losses, then you have to minus the losses, right? Okay, isolation can be done using transformer. So there are 2 types of driver circuit. In the commonly seen driver circuit without the transformer, then the function is only to do the amplification. Because in most cases, the control circuit will give you low power. Yes. But then you need to turn on the specific switch, depends on what switch that you are using. You need to select the correct driver circuit to match the switch, right? Because the control unit is giving you low voltage. You need to step up the voltage to the appropriate level using drive circuit. So this is one example of the 12-volt relay. The input from the circuit, if you see, this is the real picture of the circuit. And then inside, I think you have the transformer, okay? This is the symbol of transformer. And it says that the input from the circuit is giving you 5 volt and 0 volt. 5 volt, 0 volt is not able to turn on or turn off. You can turn off, but it is not able to turn on any practical switches. So you need to actually make it what? 12 volt. Then the relay can be on and off. So you see that the power is actually inside here. You will make from the 5 volt, 0 volt, 5 volt into 12 volt. So this is amplification from 5 volt to 12 volt. And Number two, it's doing what? Isolation by using transformer. The transformer is here. Transformer and amplification. In this example, it has both the functions fulfilled. Okay, now to amplify the voltage as well as to do the electrical isolation. Okay, this is another example of amplification. How does it work? You can read it here. Yeah, very simple. By turning on this Q1, what happened? The voltage, the current is flowing to the ground. If the voltage is 0, right, because the current is flowing to ground, so this voltage is 0. VGS equals to 0. So it turn on or turn off. If you supply 0 volt, it will be off. What is the name of this switch? IGBT, BJT, MOSFET? Quickly.
MOSFET.
MOSFET. So MOSFET needs to be turned on. At least you must have 12 volt to 15 volt. Here 15 volt. So if I supply 15 volt, positive here, not negative. Positive 15 volt, it will be turned on. Okay, how they turn on? You have to make sure that this one, Q1 must be off. If this is off, then this one will be open. Open means that this VGG will supply the current to the ground. So VGS equals to 15 volts. So when this VGS is 15 volts, provided the VGG is 15 volt, then this current will flow from D to S. Okay, that is the operation of the. So where is the driver circuit? Driver circuit is here. From VGG, RG, and this Q1, LM311. It's called the driver circuit. And this is the IGBT, this is the MOSFET. MOSFET is only here. And the external here is the driver circuit. And this external driver circuit is doing what? Amplification from the signal voltage. Let's say the signal voltage is 0 to 5 volt, giving you the control. Then the 5 volt is being amplified into 15 volts. In this case, this example, does it do isolation? No, it's only amplification. No isolation because there's no transformer involved. Okay, in this case, using pulse transformer, yes, the transformer is used to do isolation. Does it doing any amplification? It depends on the, anyone knows? What is N1, N2 here? The number of windings on the primary versus the number of winding on the secondary. If it's being stepped up, so the voltage can be stepped up. If it's being stepped down, I don't think they would do the step down voltage. It depends on the design, right? If the input is high voltage, then you step down. In most cases, the signal will be step up. So if it's the N1, if N2 is N2 is bigger than N1, so it becomes step up transformer. So it will do the amplification. In this case, yeah, amplification. Okay, and at the same time, it does isolation because of the electrical separation in transformer. Okay, another example of using optocoupler. What is this opto? Using light, you see the arrow here showing the lights. Okay, optocoupler. Does it touching any electrical touching in between the left and right, 1, 2, and 4, 3? The circuit 1 and circuit 2, does it touch any current flow? There is no current flow. Yeah, it behaves like transformer as well. So this isolation is done using without transformer, but using optocoupler, using light. Okay, you see the diode and the arrows, two arrows, transferring the signals from the left to the right, circuit 1 to circuit 2 using light. Okay, this one do isolation, but it does not do amplification, unless they have additional circuit here on the right hand side to amplify the signal. Okay, so this optocoupler function is just to do the isolation. A very small IC. That's it for the part 3, very short, isn't it? So the function is just to introduce to you what is gate driver. So when you talk about all the switches has to be controlled. When we talk about the control switches, it can be on and off. So how do you want to turn it on and off? You need the help of driver circuit to make sure that the requirement level of on and off is fulfilled. The level, where's the level? Yeah, the level. Here the level refers to the voltage here, 15 volt, 12 volt, and some switches requires the current, like you need to turn off using negative current of the anode current. These are also the driver circuit that you need to fulfill the level of requirement for on and off of the switch. Okay, anything to ask? So the last PDF here is the power losses. What is loss? Disappear. So power loss, right? Do we get it? Power loss, do we get it? No, it depends on how you want to imagine it, right? Most cases, power losses will disappear in terms of heat. So if you have one electrical device, right, you turn it on for some times, and then you touch the electrical device. What happened? It ons for a few hours already. Let's say your mobile phone, you've been using your mobile phone for gaming, okay, and then after you finish your game, you touch your mobile phone, is cold or hot?
Hot.
Hot.
Why is it hot? Because you put it in the oven?
No.
No, because of power losses that dissipated in terms of heat. So we call it dissipated or expel, or what do you call it? Disappeared in the environment. Okay, dissipated is the terms that normally we use it. In terms of heat, heat is a form of energy. So the energy that you supply in, let me draw the box, is operation. So energy input, 100%. Do I normally get the output 100%? It doesn't exist in real world. The ideal case not happening. Maximum maybe I get 90% of the input energy. And when just now we say that the energy conservation says that energy cannot be destroyed and cannot be created. So if you have input of 100%, the output should be 100% as well. But then you will only get the output, or we call it useful, or the efficient is 90%. Useful output is only 90%. Where is the balance? The balance is 10%, isn't it? 90 plus 10 is 100. So this is operation, any operation. So the 10% is not the useful energy. It is not giving me any benefits. Okay, it dissipated as heat. So this 10% is heat. We call it loss. Okay. If it is not useful energy, we consider that as power losses. So these power losses What is the impact of the losses? The losses, because it's not useful, we don't get the benefit. It will bring down the efficiency. Remember what is efficiency? P out over P in general, multiply with 100%. So your P out now is 90%, your P in is 100%, so you only get 90%. Okay, the more losses, let's say the losses increase double, become 20%. What happened to the output? It becomes 80%. So the efficiency will drops further to 80%. Okay, so in any design, we want the power losses to be high or low.
Low.
As low as possible. By choosing the good materials, like they have internal losses that very small, and you design in the right frequency range so that you don't get losses in terms of switching frequencies, etc. So that the overall design gives you good, useful energy. Right, power losses in power converters. So again, still remember what are the converters? We have rectifier, using thyristor or diode. We have a chopper. Chopper is what? Helicopter. DC to DC converter. We have inverter. Inverter is changing what to what?
DC to AC.
AC to AC.
DC AC converter. This one is AC DC rectifier. Last one. Anyone knows?
DC to DC converter.
DC DC is chopper. One more. Quiz time is a quiz. Fill in the blank. What is that?
AC to AC.
AC to AC. What's the name? Oh,
Cycloconverter.
cycloconverter. Thank you. So these are the converters. Of course, losses happen in all the converters. What are the losses? Parasitic losses. Parasitic losses. Power switches losses. Any more? Forward conduction number 3. Losses. Any more? Blocking. How many already? Blocking state losses. 4 and then 5. Switching losses. 5. Any more? No more. Okay. So there are 5 names in the power losses. 5 types of major class of losses. Let's go through again. You have parasitic losses. You have power switches losses, forward conduction, which is the on state loss, and then we have the blocking state loss, which is the off state loss, and finally you have the switching loss. So there are 5 losses of categories here. Let's go one by one. What do you mean by parasitic? We don't want them. They are parasite. Because of what? Due to the winding resistances of the inductor and transformers, dielectric losses of the capacitors, eddy current and hysteresis losses. We don't want them, but they appear to be in there. Okay, we call it parasitic. For example, you buy resistor, right? No, you buy inductor. Inductor is L. What I want inside the inductor is only the inductance, isn't it? But in real world, when you buy inductor, it will not give you only the inductance. Inside the inductor, you will have inductance plus resistance, small resistance, because this small resistance happen inside the material that you use to create inductance. We call it parasitic. Or sometimes you know that the word ESR comes in. Anyone knows what is ESR? ESR is what? Emergency? No. ESR stands for equivalent series resistance. Okay, being an engineer, you guys need to know what is ESR. Yeah? ESR is equivalent series resistance. So it link to these parasitic losses. So inside the windings, right, you have all the windings like solenoid. Inside this material that you use to do the windings, it has the resistances. So this resistances is ESR or parasitic. Okay? This one creates what? If current flows, if it is ESR, right? R. If current flows through, IR is what? Multiply with R. I multiply with R equals to voltage. But this voltage does not contribute to your useful energy. It is loss. Okay, it is not useful, and it will create as a loss happen in heat. So that is the things. But can you eliminate this resistance? Cannot. You cannot do anything because it's inside the material. So we cannot help unless you buy the material that comes in with very pure. But it doesn't happen, right? You will have a small amount as well. So number one is parasitic losses. You cannot help to reduce that. It is on the material itself. Number two is the power switches losses. What is that? It says it is significant and can be managed, of course. How do you manage this? Power switches losses? You have the power. What is your power? You can buy lah. You can go and Shopee or Lazada and find. There are so many options here. Okay, example RGBT, like if you want to buy, let's say, then you go and see voltage drop. Which one's better here? Do I buy 3.2 or 2.4? You can select. Okay, if you want high losses, then you buy the high losses. If you want to have a design a good efficiency system, you need to buy as go on and survey until you have maybe 1.0 volt. Okay, this is not all the manufactured options, right? You can go and then survey more. Let's see any more examples. Yes, this is the internal resistance that contribute to loss, R on. When it is on, current flows multiply with the R on, it will give you the voltage dropped. So do I pick the bigger one or smaller one? If you want a good efficiency, this is very big. Cannot, not good. Which one is the smallest?
The upper 0.01.
Yes, the model should be IRFZ48. Oh, this is the champion. But I need to consider as well. If I want to operate my system in 120 volt, can I use this one?
No, nothing.
Cannot, because the rated voltage is only 60. I cannot use this IRFZ48 in my system if my voltage is 120 volt. So which one can I pick? The option is only here. Can I take 100? 120 is quite near, isn't it? Cannot. Your rating must be higher than your operating voltage. So you can only choose 400 and above. So out of these options, the available, the best should be this one, 0.25. So in most cases, you have what in your design? You have trade-off consideration. It's not that you want the best, you get the best. No, there are many challenges. Okay, power switches you can manage because you can choose, right? You can survey and choose the better option that you want. It depends on the switch itself. And what is forward conduction? Forward, go front, means turn on. On. How do I draw the switch when it is on? In ideal case, the switch is closed, right? On. How do you turn off the switch when it is open? The switch is off. What is the name that we say when the switch is off? On, close or open?
Open.
Open.
So be careful, yeah. These are the names that you will see. Say sometimes say in the questions that the switch is opened. Open means what? Open means off. And when it's on means what? It is closed. On state. On state means close. The current is flowing. Okay, current is flowing. So when it is closed or on state, measure at mains and lower frequency operation. When switch is at on state, heavy forward current is conducted. Non-zero voltage across the switch. Vs on multiply with the current IF, the current that flows through the switch, multiply with the Vs, the voltage across the switch. You know that the switch is not ideal now. Where is the not ideal? Not ideal here. For example, let's take IGBT just now. Where's the IGBT? Here. Where is the VDS? Where is the voltage? Voltage. It's not given. Let's see this example. Okay, VF on. So when this IGBT is on, close, right? You will have a voltage drop of 2.4 volt. Okay, it's not ideal. If it's ideal, means it close, the voltage across the switch is 0. No voltage dropped. But in practical, any switch, you have the number of voltage drop in the switch itself. So this voltage 2.4 multiply with whatever current. And we know the IGBT is carrying medium voltage, medium current, right? What is the current that it can withstand? The current is 32 amps going to 300 amps, a lot. Let's say 32 amps times 2.4, what do you get? That one will contribute to your loss. That loss is called the forward conduction. It only happens when the switch is closed. Okay, and then it takes the Vs on, which is the voltage drop of the switch. And any more example here? This one you have to calculate by using the RDS on. Okay, you will talk about the voltage drop of the diode. Diode depends on the material, right? 0.3 or 0.7. Is this a diode? Yeah, 0. What is the voltage here? 1.1, 0.5, 0.7. Okay, depends on different materials. The voltage is different. In general, 0.3 and 0.7, silicon and germanium for power diode. So these are the forward conduction on state. What happens if it is not on? It also has power loss. Just now I turn on, you say that there is a loss. Okay, fine. Now I turn it off, also got loss. And the loss name is blocking state loss, or we call it off state loss. Remember, when it is open, you have the blocking state loss. What is this blocking state? When the power switch is at off state, it will need to withstand the high voltage, hundreds to 1000 volt. Basically, you just see that you have a voltage source here, and you have a switch here. Any current flows? The switch is open, right?
No, doctor.
No current. I is 0. But let's see from here. From the switch, if you look from the switch, Any voltage drop?
Yes.
Yes, this is called the open circuit voltage. And this voltage equals to? What is
Source.
the voltage? Yes, because there's no current, right? So the voltage of this equals to the voltage of the supply. So if the supply is high, right, if the supply is high, then the voltage that the switch needs to what? Need to support, or needs to withstand, needs to able to stand there and not die. Withstand. Okay, it's from hundreds to thousands, or maybe 10 of thousands. Very big, isn't it? So that one is known as the blocking state, off state, close. This is opened loss. Okay, the loss during blocking state. Just now was the loss during the on state. Normally on state, the voltage is small, yeah, because it is forward conduction, voltage dropped. But when it is off, the voltage is actually referring to the supply. So the voltage is high. What about the last one, the switching losses? Due to the current and voltage changing simultaneously during the switching period, the significant when the switching at high frequency. This one you need to know the diagram of this one before you can appreciate what is switching losses. We have seen this diagram before, right? Early in chapter 1. I think so. Here you are. Where is it? Here. Non-ideal switching characteristic curve. You still remember this diagram on the left? We say that when you want to turn on and turn off, this one is turn on or turn off? Where are we starting from? Let's say this region. The yellow region is on state or off state?
Off. Yeah.
Off. How do I know? Because the current is 0. No current flow is
Open circuit.
open circuit. And open circuit, we have the open circuit voltage. Now, I want to change from the current state into what state is that?
On state.
On state. Let's give it a different color, green, this one. What happened? I turn on the switch, isn't it? You turn on the switch. Immediately when you turn on the switch, does the current flow to the steady state instantaneously? No, it doesn't happen in real life. The current will go up slowly. See the current go up like hiking, right? Hiking going up until it goes to the steady state here. So from the moment of this zero current until the steady state of the turn on, it has some time, the period. This period is known as what? Power loss. Why? Because the current is rising and the voltage is falling. Current and voltage, what happens if they multiply with each other? They give you the power. So the power at the bottom here is actually the power loss. What name of this power loss? That is the name of the power loss. Switching loss. This is switching loss. It happens when you turn on and you turn off. Okay, rising and falling. Both rising and falling will give you this pump. And this pump is actually the product of I multiply with voltage. This is V, this is I. Multiply, you get the power. Okay. This is known as the switching loss. Switching loss. Okay, now if you have high switching loss, high frequency means what? Any diagram showing high frequency? No, let's draw it. Same time, This one is high frequency or low frequency?
Upper, low,
Not
what did I?
beautiful. So this one is low frequency. This one is high frequency. This one happens up and down only one time, two times. This one, 1, 2, 3, 4, 5. 5 times. Every time you on and off, I'm supposed to draw in the pulse, you know, not sine wave. Doesn't make sense. On off, right? This is normal. And then you have a very, very frequent on off. Comparatively, case A and case B, same thing. High frequency A, no, high frequency is B. Low frequency is A. Here at the time you turn on and turn off, only how many times? 1, 2, 3, 4, 5. 5 times, right? So you have 5 times of losses. This one you have 1, 2, 3, 4, 5 until you repeat. You have to count much more than 5 times. So the switching loss happens more than A. Okay, so you add up in the real life application. We need to add up everything because everything is cumulative. The switching is going on maybe 1000 cycle per second compared to 10 hertz. But then it operates all the times in terms of time for 1 hour, for example. How much actually the losses that you accumulate? A lot. Okay, so switching frequency is actually contribute to a large portion of the total losses in any system. Okay, the same pictures that shown just now, you can calculate the on time and off time and calculate, actually estimate the loss in terms of power. Okay, after finishing the number of 5 numbers, yeah, we remember 5 losses categories. Still remember what are the 5? Parasitic, switch loss, forward conduction, blocking state, and finally switching loss. Then we need to know also how to minimize the switch loss. What is the switch loss here? We are using snubbers. Snubbers is actually a circuit here used to do what? There's a function there. So how does the snubber circuit looks like? Okay, there are many types of snubber circuits, but in this course we're only focusing on one. One example of snubber circuit is called the RCD type. Why is it called RCD type? Because it only has these 3 components. If you can see the RCD. After that, finish already. So where is the RCD? First of all, where is the snubber circuit? On the left-hand side or the right-hand side? Okay, this is the snubber circuit. What is inside the snubber circuit? You have the diode, you have the resistor, and capacitor. So R, C, and D. Okay. Who is connected in parallel? RD connected in parallel and series with the capacitor. So what is this RCD? We know that we called it snubber circuit. Okay, snubber circuit. What does it do? It has function. What is the function? To protect. To protect. How do you protect? By limiting the stress and diverting the energy during the switching transition. So it helps to reduce the power loss, save. Okay, minimizing power losses using snubber circuit. Because snubbering helps to divert energy from switch to a lossy, high losses, or non-lossy, low losses circuit. So zero voltage or zero current switching. You want to switch that just now, right? We want to switch. This is the operation of switching from on and off to on, the transition. How to make it zero? 0 is like this, instantaneously. So the voltage, this is the voltage, high voltage 0. How to make it 0 voltage switching? You switch at the 0 point. When you switch at 0 points, 0 times any current, what do you get the power loss? 0, right? Because one of the component voltage is 0. And if you're switching it at 0 current condition, what happened to the power loss? Still 0, because P equals to IV. Any of the component here is 0, then eventually the power will be 0. So 0 voltage or 0 current switching contributes to 0 losses. But how to make it happen at 0 voltage and 0 current? That is a complex control, okay? But it can be done, yeah? It can be done at 0 voltage, 0 current switching. So just now we said the snubbers is used to reduce the stress, yeah? To limit the stress. Stress here actually refers to what? Voltage level. Bring down the voltage level or current. Example of stresses, maximum transient voltage, maximum transient current, rate of change of switch, rate of change of switch in terms of voltage and current. Okay, rate of change like this, or like this. So this the gradient. This is the gradient. Di over dt, dv over dt is the gradient. Which one? The gradient is high. C, the gradient is very steep, so very high. Okay, you don't want that because this is too spiky. We want it to be gradual. This is called what? Overshoot. It also contributes to loss, and overshoot, we don't want that. It creates a lot of problems. So you see this example of a waveform here. From 0, I start to, okay, I turn on. Suddenly, the voltage going up until here, and then it rise. Okay, it's playing what? Oscillation. Oscillating. Okay, overshooting. This one? Undershooting, right? Undershooting. Overshoot, undershoot. Okay, this dotted line is actually the one that I want. My final steady state value. But before you reach the steady state, you have this overshoot, undershoot, and then oscillate. Okay, if you still remember your control subject, you learn about what? Under, over, critical, right? Damping. Okay, these are all the characteristics of transients. You have under damp, over damp, critically damp. Ideally, we want them to be critically damp. Okay, okay, on. And then what do I get? Okay, one on, and then this is the critically damp. Okay, finish. No. Okay, this is not so beautiful. I don't want it to be slow like this and never reach the steady state. The one. Takes time, right? Waste of energy. And I don't want it to be too fast, otherwise it will be overshooting. I want it to be in the middle, just right, very quick and no oscillation. So this snubber circuit can help me by doing what? By changing the waveform of this original overshooting and undershooting and transients into a beautiful slowly rise. Not too slow. You cannot design that give you too slow, right? Under damp. You know, over damp, we don't want that. So it helps to reduce the rise and dampen the high voltage spike. So the high voltage spike finish cannot eliminate it. So that is the function of this RCD. What else that I need to say here? Okay. So original, just now we have here, okay, original. And then it helps to reduce the rated voltage into very nice and slow rise. Okay, the spike. Sometimes if the spike is too high, what is the impact? This spiked. Okay. If it is too high, right, it may contribute to what? Damage, yeah, of the switch or the surrounding circuit, because the voltage is too high, right? So we don't want that to happen. So you need to have a snubber circuit to help you to reduce the voltage stress. That is what we call it, voltage stress. Okay, during turn on you have the current stress. Turn off, you have the voltage stress. And then if it is not this on and off state, also you have the dynamic changes, okay, during the transients of the slope. Is too gradual or is too steep? These are all the example of stress. Okay, so now if you change the parameter here, what is the parameter that we can play with? Remember, where is the RCD? RCD is here. RCD is number circuit. RC and RCD. RD parallel in series with the capacitor. What is the parameter that we can play around with if we're talking about the damper of damping the voltage? Which parameter that we can play with? The capacitor. Okay, you can play around with the capacitor. Can you see the diagram here? We have three diagrams here, A, B, and C. Okay, this A, B, C, right? If you look at the power, this is the power loss. And the power loss become reduced. And the C, the power loss is very small. And that is the effect of different C. C1, C2, C3. What do you think? C1, C2, C3, which one is having the bigger C? Any? The R and D is the same, yeah, or for these all three cases. What I'm changing is just the values of the capacitor. So C1, C2, C3. So C1, C2, and C3. So which one is big? What arrow should I take? This one or this one? Anyone? C3 is bigger than C2 or C3 is smaller than C2? And go on.
Bigger.
Which one is bigger?
C3.
C3 is bigger than C2 and C2 is bigger than C1. Is it like that? Yes. Voltage is actually can be support or can be dampened by capacitor. So if you have a big capacitor, it's like a water tank, right? How long do you need to fill in the tank if the tank is big? Longer time, isn't it? So the time that you need to fill in the tank until it becomes full, right? That is the amount of time. If my tank is big, water tank, big, C3. If your tank is small, C1, so the time that you requires to fill in the C1 is what? Very fast. Okay, so this is the voltage that you're saying here. If you have the voltage, where is the line? Okay, so this is the change of the voltage. Very quick, slower, because you increase the size of capacitor. It becomes very, very slow when you have a capacitor is very big. So you can imagine with the tank, you need to fill in the tank until the water full. So you take a long time. If the tank is so small, so the time is very short accordingly. Okay. So in RCD, you can play around with the C parameters in terms of the size of the capacitor. If the size of the capacitor is big, then it will become very gradual rise. What happened? Your turn on and turn off transition will be long, but at the same time, it reduces the loss during the switching. So which one is good? It actually depends on your design, right? Just now we have the word what? Trade-off. Which one that actually you want? It's very difficult to have ideal case. You want it to be very fast, switching fast on and off, but the losses is high. You want it to be very slow, but the switch, the losses very low. Which one? Then you come to a balancing point, maybe inside. You would take this one, trade-off, okay, in the design, okay, in the middle. You cannot fulfill every parameters. You need to decide on which you want to take. There's no 100% perfect case in practical. That's why practical, you have so many things to consider. Ideal, easy. Practical, not so easy. There are so many things. 1, 2, 3, 4. Okay, all the characteristics. Okay. Any questions so far?
No question, Doctor.
Right. Let's continue a little bit on the cooling. Very hot. Why is it hot? Because all the losses that we mentioned, 5 losses characteristics and the snubble circuit as well, they all contributes to heat dissipation. And when you have heat, right, you need to expel the heat, or you need to be very good controlling and managing the heat. Otherwise, the product or the device may be damaged, or the life of the product will reduce or shortened. How do we cool down the switch? How do you cool down your laptop? You buy a fan and put it below the laptop, is it? Okay. Same thing, you can do it for the switch. Put a fan for the switch, but it's not practical. What actually we can do to help to cool down the switches? You can put in a big fan. Is it a fan? No, it's called heat sink. Heat sink is just a fin of conductors, help to dissipate faster the heat to the environment. Okay, these are all the fins, yeah. And different types of fins that you can see. If you notice that in your house, right, the refrigerator, inside the refrigerator is cold, but if you go to the back of the refrigerator, is it cold or hot? And you can see that there is a metal fins, metal we call it wire or fins at the back of your refrigerator. That is actually heat sink that helps to dissipate the heat quickly to the air. Okay, example of cooling by liquids. If it is required faster, faster than the heat sinks, then you can put in liquids, helps to cool down the condition and environment. But then, of course, if you have these things, the cost of doing it is very high. It can be done also, by oil or water to cool down the power switch. Heat must be transferred from the device to the cooling medium to maintain the operating junction temperature within the specific range. Yes, if you still remember, all the products that we have in the world, they have their own rated specific condition, rated condition or a rated specification. Specs. So if I say that you buy the switch that can operate up to 60 degrees C, but then you don't do this cooling system, the heat will be accumulate and the temperature will rise, and it go to 70 degrees C, then you use it for a few days, then it already damaged. Okay, so maintaining the temperature within the specification is important to ensure that the life of the device is prolonged. Otherwise, you will need to replace or buy a new switch from time to time. Okay, all right. With that, we have finished everything on chapter 1 already. Thank you. Any question?